Welcome back. In today's video, we are going to talk about matrix inverses. So in our last video, we talked about the operations addition, subtraction, and multiplication with matrices. We didn't talk about division, and that's because matrix division doesn't exist. But what we do have are matrix inverses, and so we can accomplish some of the same things. So let's get started by looking at some comparisons with real number operations. So let's look at the equation 2x equals 10. All right, so let's say we wanted to solve for x here. Now, it's probably been a really long time since you've thought about how to solve this. You know how to solve it, and you probably don't even need to think about it at this point. Divide by 2, x equals 5, right? You would have gotten that right away. But it's probably been a little bit since you've thought about why that worked. The reason why that works is because 2 divided by 2 on the left side there gives us 1x. And 1 has a special property, and that's when we multiply that 1 times something, we just get that same something. So 1x is really just x equals 5. And that's why it works. In this case, the number 1 is called the identity. So it is the real number identity. It is the number that we can multiply anything by and get that same something. So 5 times 1 is 5. 7 times 1 is 7. 10 times 1 is 10, so forth and so on. So the matrix identity is very similar. It's the thing we can multiply matrices by to get the same thing. So with a matrix, it's the letter I for the identity. And the 2 by 2, I2, the 2 by 2 identity is 1, 0, 0, 1. And so this matrix, if we multiply any matrix that can be multiplied times this matrix, we're going to get that exact same matrix out the other side. So for example, we could multiply, we'll just do 1, 2, 3, 4 times the matrix 1, 0, 0, 1. So when we multiply matrices, we multiply the rows of the left matrix times the columns of the right matrix. So we would do 1 times 1 plus 2 times 0. So that's 1 times 1 plus 2 times 0, that's 1. Then we'd multiply the first row times the second column. So 1 times 0 plus 2 times 1. So that's 2. We then multiply the second row times the first column, 3 times 1 plus 4 times 0, so that's 3. And then finally, the second row times the second column, 3 times 0 plus 4 times 1, that's 4. And so we get the exact same matrix when we multiply. So just like we do when we multiply a real number times the number 1. So there are infinitely many identity matrices. So the 2 by 2 is one example. We could have a 3 by 3 identity matrix. That would be I3. And that would be 1, 0, 0, 0, 1, 0, 0, 0, 1. What they all have in common is they have a diagonal of 1s that goes from top left to bottom right and zeros everywhere else. There's also a 1 by 1 identity matrix, I1, and it is just the number 1. So that is the matrix identity. And the matrix identity has a property, a very special property. We talked last time that when we multiply two matrices, A times B does not equal B times A. As a general rule, we cannot rearrange the order of multiplication like we can with real numbers. 2 times 5 is the same as 5 times 2, but matrix A times matrix B is not the same as matrix B times matrix A. That is, except in the case of the identity. So the matrix A times I does in fact equal the matrix I times matrix A. So those can be multiplied in any order. So that is one of the exceptions to the rule that we cannot swap the order of those two matrices. All right, so now that we have defined the identity, let's go back to the equation that we were working on just a little bit ago, 2x equals 10. Now, let's pretend that the division operation doesn't exist. So how could we solve this equation if division didn't exist? Well, there's another way we could solve this, and that is by multiplying both sides of the equation by 1/2, which is a little kind of cheating because 1/2 is 1 divided by 2. But anyway, the main operation we're doing here is multiplying. And so what happens when we multiply 1/2 times 2 is we get 1x equals 5. And of course, 1x is just x, so we get x equals 5. So again, we have our solution. In this case, that 1/2 is called the inverse. So the inverse is the number we can multiply a number by to get the identity. And the identity, remember, with real numbers, is the number 1. So for 2, its identity is 1/2, because when we multiply them, we get 1. The inverse of 7 is 1/7. When we multiply those, we get 1. The inverse of -3/4 is -4/3, because when we multiply those, we get 1. So those are inverses. When we multiply the inverse times the number, we get the identity 1. And so with matrices, it works the same way. The matrix inverse is written as a to the -1 power, is read as A inverse. And when we multiply A times its inverse, A inverse, we get the identity matrix I. And this is one of the other exceptions to that rule in that we can do this in either order as well. So A inverse times A is also the identity matrix I. So the inverse is the thing we can multiply a matrix by to get the identity I. All right, so why is that useful? Well, let's take a look. Let's say we had a equation, ax equals b, and we want to solve this for x. Well, what we can't do is divide both sides by a. That does not work because there is no division for matrices. However, we can multiply both sides by the inverse. So the way we would do that is we'd multiply A inverse on both sides. Now, we have to be really careful here. What we started off with was AX equals B. On the left-hand side, we put A inverse to the left of AX. So what that means is that we also need to put A inverse on the left-hand side of B, because remember, when we multiply matrices, the order that they're multiplied is important. If we swap the order, it changes things. So if we had written this right-hand side of our equation as B times A inverse, that would not have been the same thing. So it's really important that we multiply matrices in the right order. All right, on the left-hand side there, we've got A inverse times A. That's going to give us I times X equals A inverse B. And then I times X, remember I is like the number 1. It's the identity. So that just gives us X equals A inverse times B. So we can solve for X by multiplying by the inverse, just like we solved for X in 2X equals 10 by multiplying both sides by 1/2. Exact same idea here. So what does this do for us? Well, this gives us another method that we can solve systems of equations by. So let's take the system of equations 2x plus 3y equals 4 and 4x plus 5y equals 9. What we can do is plug this into, or manipulate this into a matrix equation. And so what that'll look like is a matrix A that will be the coefficients. So it won't be the exact same as we were doing when we put it into an augmented matrix. This will be a little different. We'll have a matrix just for the coefficients, 2, 3, 4, and 5. We'll have a matrix for the variables, x. So that's a capital X, made up of lowercase x and lowercase y. And then that will equal a matrix B, which is the constants, 4 and 9. So if we multiply these, we can see why this would work. Remember, when we multiply matrices, we multiply the row of the matrix on the left times the column on the right. So that would be the first column times the row, or the first row rather, times the column. 2 times x plus 3 times y equals 4. That's our first equation. And 4 times x plus 5 times y equals 9. That's our second equation. So this matrix equation is equivalent to that system of equations. And we can solve it by multiplying the inverse of A times B, just like we figured out right there. So we can solve this system by multiplying the inverse of matrix A times matrix B. So let's do that in our calculator. All right, so let's go to matrix. We'll go over and edit matrix A, which will now be a 2 by 2 matrix of 2, 3, 4, and 5. And then we'll edit our matrix B. So actually we gotta quit out of there. All right, now we go back over to edit, down to matrix B. So matrix B is going to be a 2 by 1 matrix, 2 rows and 1 column. So 4 and 9. All right. So we can solve this by multiplying the inverse of A. So let's select A. So second matrix, select matrix A. The matrix button, if we don't press second first, that is the inverse button. So x to the negative 1. So that's A inverse times matrix B. And so that is our answer, 3.5, negative 1. Now, the MyLabs program will generally want you to write your answer as a fraction instead of a decimal. And the calculator can convert those for you. So 3.5 is 7 halves. And we can figure that out by pressing the math button and then selecting the first option, fraction, and then press enter. So that tells us that it's 7 halves and negative 1. So, and that is that matrix right there is this matrix right here. That's x. So x is is 7 halves and y is negative 1. So this is just another method we have of solving systems of equations. So we can put it into a 2 by 3 matrix and use the RREF function, or we can put it in as a separated matrix A and B and multiply the inverse of A times matrix B. Now, this, if you just have one system, it's often faster to put it in as a 2 by 3 matrix and use the RREF function. But if we have multiple systems, this method is actually a little quicker, and that's actually where the benefit of this method works. So let's say we've got the system 2x plus 3y equals 1, and 4x plus 5y equals 4, and the system 2x plus 3y equals 2, and 4x plus 5y equals 5, and the system 2x plus 3y equals 3, and 4x plus 5y equals 6. All right, so we have three systems of equations here, but the left-hand side of every system is the same. 2x plus 3y, 4x plus 5y. So when we have repetition like this, what we can do is combine this into a single matrix equation. So our matrix A, our coefficient matrix, stays the exact same. It's 2, 3, 4, and 5. Now, if those changed at all, we couldn't use this method. So these have to be 2, 3, 4, 5 in every single system. Otherwise, this method's not going to work. All right, so A is 2, 3, 4, 5. X, we're now solving for all of the x's and all of the y's all at the same time. So we'll actually number them. So these will be x1 and y1, and then x2 and y2, and x3 and y3. So our first system of equations, we have x1, y1. Second system of equations, x2, y2. And third system of equations, x3, y3. So that matrix X will be x1, x2, x3, and then y1, y2, y3. So it's going to solve for all of those all at the same time. So each column represents a different system of equations. So the first column, x1, y1, is that first system of equations. The second column, x2, y2, that's our second system of equations, and so forth and so on. So we can do this for infinitely many different systems of equations, so long as we're using the same coefficient matrix A. So we'll set this equal to our matrix B. So we've got B is 1. So we'll put them in vertically just because it'll make our system a little easier. So 1 and 4 in the first column, 2 and 5 in the second column, and 3 and 6 in the third column. So the matrix 1, 2, 3, 4, 5, 6. All right. So now we can solve all of this by multiplying the inverse of A times matrix B. All right. So in our calculator, if we go second matrix, over to edit, matrix A. We can see that's already the matrix we have because it was the same coefficient matrix that we used on the last system. So we can just keep that. So let's quit out of there and let's go to matrix B and we'll edit that one. So instead of 2 by 1, which it would be if we were solving a single system, it's now going to be 2 by 3 since we're solving for 3 systems at the same time. So we've got 1, 2, 3, and then 4, 5, and 6. All right, so we'll quit out of there. We'll type second and then matrix. We'll select matrix A, inverse, times matrix B. And so it solved all 3 systems at the same time. Again, we'll use math and then fraction to change these into fractions. So the first system of equations, x is 7/2, y is -2. The second system of equations, x is 5/2, y is -1. And the third system of equations, x is 3/2 and y is 0. So there's going to be a couple homework problems where you're going to have multiple systems of equations that are, the coefficients are all the same, and then you have different constants. And so you can do those in any way you want. You can use RREF multiple times, and that works just fine. So we could have taken this system, we could have taken the first system, put it in as a 2 by 3 matrix, used RREF. And then put in the second system, repeat the process. Third system, repeat the process. Using the inverse of the coefficient matrix is just a little faster. But if you ever forget how to use that method, you can always go back and use the RREF method. This unit is all about solving systems of equations. So for lots of different problems, there are lots of different methods you can use to solve the problem, and you'll come up with the same answer every way you do it. So, all right, let's look at one more example. of solving a matrix equation. So let's say we've got ax minus c equals bx minus d. And we want to solve for x here. So just like with real numbers, we want to get everything with x's on one side, everything without an x on the other side. So let's add c to both sides. So plus c plus c. So it's going to give us ax equals bx minus d plus c. All right, and then we'll subtract bx from both sides. So that's going to be ax minus bx equals negative d plus c. All right, on the left-hand side, we now have two terms with x's. So again, very similarly to how we would do if we were dealing with real numbers, we're going to factor out an x. Now, here's where we have to be careful. With real numbers, generally we factor the x out to the left side. It doesn't matter how we factor it out with real numbers. It does matter with matrices. So x is on the right-hand side of A and the right-hand side of B. So when we factor out an x, we have to write it as the quantity a minus b times x. X has to stay on the right-hand side because that's where it was before. All right, so that's going to equal negative d plus c. And our last step is going to be multiplying both sides of the equation by the inverse of a minus b. So we'll do a minus b inverse times a minus b x equals, and again, we need to multiply things in the same order. So the inverse on our left-hand side of our equation went on the left of the quantity a minus b times x. So it also needs to go on the left-hand side of a minus, there we go. On the left-hand side of negative d plus c. So a minus b inverse times negative d plus c. Now, this right here is one of the common mistakes that I see on this question. The way I have it written right now, this is a minus b inverse minus d plus c, not times minus d plus c. We're multiplying the inverse on both sides. So we have to put minus d plus c in parentheses, otherwise it's not correct. All right, on the left-hand side, a minus b inverse times a minus bx. A minus b inverse times a minus b gives us I times x equals a minus b inverse times negative d plus c. And we know I times x is really just x. So we've now solved for x. X is a minus b inverse times minus d plus c. So this is how we can solve matrix equations. And these actually are things that are used in the real world. There is a matrix equation, x minus ax equals d, that is used for what are called Leontief models in economics. It's used for modeling the commodities of different economies. And the way you solve it is very, very similar to how we just solved this system of equations. So this isn't something we just invented for math's sake. It is something that is actually used in the real world. So, all right, that's it for this video. I'll see you next time.